and 13. Okay, so notes 8.11 is the washer method, so it's revolving around the x or y axis. So this is called the washer method, is because when we are finding the area and then eventually the volume of these things, there's going to be a space between it, which is going to form a washer. Does everyone know what a washer is?
It's like
Like
the thing that goes on
It's like the little circles.
Like the one that the user goes into the
it goes on
No.
the bolts.
Yes, on the bolts and washer thingies. It's like a tool, whatever it's called, okay? It looks like this. It looks like a donut, okay? So we have the area that is this whole outside part. Are we ready? Okay. So we're going to find the volume of the region enclosed by y is equal to square root of x and y is equal to x squared, and it's rotated about the x-axis. So same thing that we were doing the other day. We just know now that there is going to be a space between, and so we use what is called the washer method. So the very first thing we need to do is we need to draw the mirror image of the function across the x-axis. So for example, this square root of x is going to be mirrored this way. And then the x squared is going to be mirrored in the other direction. Okay. So what we did is we took this original area here between these two functions and then mirrored that area on the other side of the x-axis between those two functions. So if we were to take those two areas and rotate it around the axes, since there's a space between those two areas, what is happening here is it's forming a washer shape. Okay, so we have a small circle and then we have a larger circle. And since we're looking at the x-axis, that means that is where we are going to find our boundaries. And so we have here that it starts at 0 and it's going to go up to 1. Where's the intersection of that first area? At 1. Okay, so when we're writing our integration, this is going to be integral from 0 to 1. Okay, we're still dealing with circles, so we're still going to do the area of a circle, which is pi r squared. Okay, but since we have two circles here, we're going to actually do the radius of the large circle first, and then the radius of the small circle. So the radius of the large circle is going to be what's touching the outside function, and if you look at this point here, notice that the outside function is going to be the square root of x. So right here, this is the outside function. Okay. So then I'm going to do the square root of x squared minus, and then I'm doing pi r squared again, but I'm now using that smaller radius, which is going to be the inside function. So when I mean inside function, it's this part right here. Okay. And so that is going to be x squared squared dx. Okay, from here we can simplify this by taking the GCF of pi out and then putting pi outside of the integral. So this is pi integral of 0 to 1. And then I can simplify my x's. So square root of x squared is x, and x squared squared is x to the 4th. So I have x minus x to the 4th dx. This is just the simplified version. And then from here, if I'm going to integrate, I have pi and then x squared over 2, the integral of x, minus x to the 5th over 5, the integral of x to the 4th. Solved at 0 to 1. You would plug in 1, then you would plug in 0. Magic of algebra. You get 3/10 pi. So ultimately what we did is we used the volume of a solid revolution of washers formula, and that is volume is equal to the integration of a to b of pi times capital R of x squared dx minus the integral of a to b pi of little r of x squared dx. Okay, but notice when we did our first step, instead of writing it as two integrals, we know based on the properties of integrals that we can combine it into one. So we kind of skipped that whole step there. And then also, in our next step, we took out pi. So if you look on the next part here, it's going to simplify it for us. So it's going to take out pi and then combine it into one integral. And this gives us capital R squared minus lowercase r squared dx, where capital R of x is the radius of the outside function and lowercase r of x is the radius of the inside function. Okay, any questions so far? Okay. So if I look back at this first example, I want you to keep in mind that since this is based off the axes, so x or y axis, okay, technically what we are doing is we are taking 0 minus a function, or a function minus 0, because the x-axis and y-axis is at 0. Okay, so when we get to the next part of the notes, when we're actually dealing with a rotation around a line, okay, that is where that minus is going to come from. So think of these functions here as minus 0, but we don't have to write that minus 0. So number 2 says find the volume if the region enclosed by y is equal to x squared plus 1 and y is equal to 2x plus 1 is rotated about the y-axis. So that since this is talking about rotation around the y-axis, that means I need to take these equations and get x by itself. Okay, so again, this is rotation around the y. And I'm going to take y is equal to x squared plus 1. When I get x by itself, that's me subtracting 1 and then taking the square root. So x is equal to plus or minus the square root of y minus 1. And then y is equal to 2x plus 1. If I get x by itself, I'm subtracting 1 and then dividing by 2. So I have x is equal to y minus 1 over 2. Okay, so once I get these in the correct terms, so in this case in terms of y, where x is by itself, then I'm going to look at my graph and I'm going to make sure I draw the mirror images reflected over the y-axis. But notice my quadratic, since it is symmetric, already has a reflection across the y-axis, so I don't need to mirror that one. The only one I do have to mirror is going to be the line. Okay. So then what I end up with is these two areas here, so my original one and then my mirrored image one. And if I was to imagine those two areas revolving around the y-axis, so spinning around it, it's going to create a washer form. Okay, so where I have my smaller circle and then my larger circle. Okay, so from here, since I'm looking at the y-axis, I'm going to identify my boundaries. So looking at the y-axis, where does this function start and where does it stop? 1 and 5. Okay, so when I write the integral, and I'm going to be using the second formula where they already took out pi. So I say volume is equal to pi integral of 1 to 5. Okay, then I do capital R of x squared, which is my outside function. The outside function is going to be this function right here, the curve. That's on the outside. Okay, the curve is represented by the x is equal to plus or minus square root of y minus 1. But since we're squaring it, it doesn't really matter if it's positive or negative, so I'm just going to write the square root of y minus 1 squared. Then I'm going to subtract the radius of the inside function, and the inside function that is closer to my circle that I drew is going to be the line. So I have minus y minus 1 over 2 squared dy.